Hello, my name is Christian and I'm going to show you how to tune a PID control for a temperature process. We're going to tune the using the empirical method, which means that we have to find the constant just by watching the step response behavior. First, we define the zeros and the poles of our function. Having this, we get the transfer function and we define a unitary feedback, which means that the system is a closed loop one. So we define systema, feedback, planta, and the unitary feedback. And we plot this and let's see what happens. Okay, here we have the step response. We can see the characteristics. For example, we can see the settling time and the rise time. Here we can see. So we're going to find, first we are going to find the proportional constants. We're going to use a function from MATLAB, which is the PID 1. Let's define the constants, the proportional constant. Let's put it at 0. The derivative constant, 0 as well, and the integrative constant, 0. Then we define our function, this PID, and it goes as follows: P I D. Now we're going to do this, which means that we are going to multiply the function PID for the planta. And we define the unitary feedback, and we plot this, and let's see what happens. Okay, grid on. Let's define the proportional as 1. And well, we're not going to plot this. Run the program and let's see what happens. Okay, here we have the response control. And here we're going to compare. Let's give the proportional a high value, for example 10 or 20. Either one is correct, and let's see what happens with the response. We see an oscillation, and let's see the settling time and the rise time. We see the rise time is low compared to the step response without any controller, and the settling time is almost 250 seconds. We have to try to improve this. What if we define the proportional constant as 30? Let's see what happens. Let's see the characteristics. Settling time, rise time. If we compare the rise time to the other proportional constant, it is much less than the other one, but the settling time increases. So once done this, let's define the derivative constant. Let's define it as, let's start by 5. Let's see what happens. If we can see that it looks like the step response, but we have this peak. How do we improve that? Let's define a little and small value for the integrative constant. No, let's put 5 and this 15. The computer is not responding. Okay, let's lose 15, 5. Let's see what happens here. Okay, here we have a good response. We define it 30 as proportional, 15 as derivative, and 5 as integrative. But how do we know if it is correct? Well, now let's compare to the step response without any controller. And let's graph. Okay, here we have. Let's see the characteristics, the settling time and the rise time. You see, the rise time is very small compared to the one without any controller. And the settling time, it is much better compared to the step response without any controller. So this is our temperature process with a PID controller, and it is tuned. And here we have another transfer function, and this is to control the pitch angle from an airplane so that the airplane keeps horizontal. This is the transfer function, and this is the aileron, which works as a proportional constant. And we have 3 conditions. The steady state error constant has to be greater than 130. The overshoot has to be less than 15%. And the peak response has to be less than 0.7 seconds. We will resolve this exercise using the state variables. Here we define the zeros, the poles, the gain, and this is the command to transform to state variables. Here we define the peak response, the overshoot, and this is the equation to calculate sigma and the natural frequency. Once we have the natural frequency, what we have to do is transform this into a second order transfer function. Then we get the roots, we define the poles. The system is a 4th order system, so we have to add 2 more poles. This command occur is used to define the vector of the gains. We define here the rest, and let's see the response. Okay, we have, let's see the response. This only have this system is only tuned with a proportional constant. It is only a P control, since an airplane has a very slow response. Let's compare the characteristics: the peak response, the settling time, and the rise time. You see, the peak response is less than 50%. The rise time, well, it was not specified in the exercise, but anyways, we have 0.22 seconds, and the settling time, which is almost 1 second. Okay, here we have the overshoot, which is 15%, and the peak response, which is half a second, and the exercise asks 4.7 seconds. So here we have our PID tunes, and that's it. Thanks for watching this video.